Now we're going to see lead poisoning and sideroblastic anemia. Sideroblastic anemia is due to defect in the synthesis of protoporphyrin ring. So let's quickly remember this protoporphyrin synthesis. We have glycine and succinyl-CoA. This produce aminolevulinic acid by the aminolevulinic acid synthase. Then the aminolevulinic acid dehydratase converts it to porphobilinogen. Then the hydroxymethylbilane synthase or uroporphyrinogen synthase or porphobilinogen deaminase converts porphobilinogen to hydroxymethylbilane or pre-uroporphyrinogen. Then hydroxymethylbilane is converted to uroporphyrinogen 3 by the enzyme uroporphyrinogen 3 uroporphyrinogen 3 co-synthase. Then it's converted to coprorinogen, then converted to proporphyrinogen, and the proporphyrinogen is converted to protoporphyrins. And the enzyme that both of these reactions is the proporphyrinogen oxidase. And the enzyme that puts the iron to the protoporphyrin rings is the ferrochelatase. And here I miss one enzyme. Hydroxymethylbilane to uroporphyrinogen to coproporphyrinogen is the uroporphyrinogen decarboxylase. Alright, now in lead poisoning there is inhibition of the enzyme aldehydrase and ferrochelatase. So there is no production of the heme group, not because there is no iron, but because there is no ring of protoporphyrins. So in the iron studies, we will see increase in the iron, decrease in heme, that would be the anemia, decrease in hemoglobin. Because there is a lot of iron, there will be increase in ferritin and increase in the percentage of saturation of the transferrin and a decrease in the total iron binding capacity, because if there is increase in the percentage of saturation of the transferrin has less capacity of binding to iron because all the spaces are being occupied. This is the only anemia in which there is increased iron, the sideroblastic anemia. This sideroblastic anemia due to lead poisoning was because lead inhibits aldehydrase and ferrochelatase, but other conditions that lead to sideroblastic anemia is congenital deficiency of some of these enzymes. The most common would be allosyntase, and also the deficiency of vitamin B6, because vitamin B6 is a cofactor for this enzyme. Usually we'll see this, for example, after isoniazid treatment or linezolid. Linezolid also could lead to sideroblastic anemia. Specifically the lead poisoning presents in a child or adult after exposure to lead. It could be in old houses or batteries or houses with old painting, etc. In the adult is kind of confusion, abdominal pain, more like that, and peripheral neuropathy, wrist or feet drop. And in the child is encephalopathy, sometimes abdominal or gastrointestinal distress, and sometimes the neuropathy. It's very, very important to detect this, especially in the children. And the treatment specifically for lead poisoning would be with ETSTA dimercaprol. And for children, we could also give succimer. But this is for lead poisoning. And in lead poisoning, there is also inhibition of the degradation of RNA. And so in the blood smear, in the peripheral blood smear, we will see these aggregates of RNA that would look like a basophilic stippling in the red blood cell. And in the bone marrow, we would see that the red blood cells are full of iron. So we will see a ring of iron, and these are called sideroblasts in the bone marrow. The most accurate test of a sideroblastic anemia is the sideroblast. And other things that can lead to sideroblastic anemia would be alcohol consumption, because it inhibits the allosynthetase enzyme, and some myelodysplastic syndromes leads to this sideroblastic anemia. This sideroblastic anemia also can progress to myelodysplastic syndromes or to acute lymphoblastic leukemia or acute myeloid leukemia, some leukemia. So in the refractory cases, we would need to treat the sideroblastic anemia with bone marrow transplantation. And remember that this is the only anemia in which we have increase in iron. Also, in the lead poisoning, there are characteristic lines that are seen on the chest X-ray of bones and in the gingiva.